dispatch with variance. And Youngmi Park is going to give the talk.
Yeah. Thank you for the introduction. Yeah, this talk is about polymorphic symmetric multiple dispatch with variance. I'm Kyunghee Park, and it's a joint work with Jae-min Hong, Guy Steele, and Seo Kyung-mil. As you all may know, method overloading allows multiple method declarations with the same name. So the methods that logically perform very similar tasks can be defined with the same name, but with different names of parameters or different types of parameters. Let's assume sorted list extends list, and we have these 4 add method declarations. And let's say we have 2 variables, A and B, with static types of list and sorted list, and dynamic types of both sorted list. For an add method call with A and B as argument, the language needs to decide which method declaration to invoke among the overloaded methods. At compile time, static overloading resolution chooses a method to invoke based on the static types of the arguments. And at runtime, dynamic overloading resolution or dynamic dispatch chooses a method to invoke based on the runtime types of the arguments. Let's now consider a slightly different set of overloaded methods to see different kinds of dynamic dispatch. So the parameter types are now list list, list sorted list, and sorted list list. First one, single dynamic dispatch chooses a method to invoke based on the runtime type of a single argument, which usually is the receiver. So in a language with single dispatch, static overloading resolution is used to disambiguate among the overloaded methods. And then at runtime, by looking at the runtime type of the receiver, variable A in this case, it first determines which class it belongs to, and then among the overloaded and possibly overridden methods, it chooses an appropriate one that was determined at compile time. Asymmetric multiple dispatch chooses a method to invoke based on the runtime types of more than one arguments in a specific order, which usually is left to right order. So among the method declarations that are applicable to the runtime types of the arguments, it chooses the most specific one by considering the parameter types in left to right order. The last one, symmetric multiple dispatch, chooses a method to invoke based on the runtime types of more than one argument, but here by considering all of them equally. So, yeah, but in this case, since neither of the second and the third declaration is more specific than the other, we need another disambiguating method declaration. And since the last one is the most specific method declaration applicable to the runtime argument types, this method call is dispatched to this last declaration. Okay? Oh, sorry. As you've seen in these examples, compared to other kinds of dynamic dispatch, symmetric multiple dispatch makes an intuitive and uniform choice among the overloaded methods. However, there is no free lunch, and there are a few things to take into account when the language supports symmetric multiple dispatch. Suppose a class C extends class B, and there are these 2 overloaded methods, and we have 2 variables, C1 and C2, with static types of C and B and dynamic types of both C. At compile time, static overloading resolution chooses the second method declaration, and the static type of the method call expression becomes C. But at runtime, since both the declarations are applicable but neither is more specific, this method call is ambiguous. Therefore, we need a disambiguating method declaration again, and the runtime type of the method call expression may become B. But then, this method call breaks type soundness because the type was not preserved. By modifying the return type of the disambiguating method declaration, we now finally have a valid set of overloaded methods. So for a valid set of overloaded methods and its correct resolution at runtime, the language needs to check at compile time restrictions called overloading rules. And yeah, the parameter types must meet some requirements to ensure the existence of the unique most specific method declaration. And the return type must ensure type preservation. And then among the method declarations in a valid overloaded set, dynamic dispatch mechanism must make a correct choice at runtime. Expressive language features often add various possibilities to make the overloaded method ambiguous and dynamic dispatch complicated. One such feature is multiple inheritance. And multiple inheritance allows, as you know, one class to extend multiple classes to make the code more modular and reusable. For a variable C with runtime type of C, both the declarations are applicable, but neither of them are more specific than the other. So this call is ambiguous, and we need a disambiguating method declaration, which is more specific than both the first two declarations. Another such feature is parametric polymorphism or generics, and this introduces type parameters in class and method declarations. For example, consider these overloaded methods. Their parameter types are respectively list P, where P is a subtype of A, and list P, where P is a subtype of B. For this sort method call with runtime argument type of list C, again, both the methods are applicable, but neither is more specific than the other. So we need a disambiguating method declaration, which is more specific than the first one. And here, in the presence of method type parameter, dynamic dispatch must not only choose the most specific method declaration, but also infer appropriate type argument for the chosen declaration. The last feature is variance, and variance defines additional subtype relations between different instances of a polymorphic type. Developers can label their class type parameters covariant, contravariant, or invariant. And a covariant type parameter preserves the subtype relation between its type arguments, while contravariant type parameters reverse the subtype relation of its type arguments. An invariant type parameter ignores the subtype relation between its type arguments, thus it does not define any additional subtype relations. Let's revisit the ambiguous sort method example again. But this time, with covariant list, we can define the sort method with the same parameter types in a simpler way. For a sort method call with static argument type of list A and dynamic argument type of list C, the static overloading resolution chooses the first declaration, and the static type of the expression is sorted list A. And at runtime, both the methods are applicable to the runtime argument type list C, but neither is more specific, so this call is ambiguous. So if we add a disambiguating method declaration in an intuitive way, the method call is dispatched to this last declaration, and the runtime type of the expression may become sorted list C, but then this does not preserve type. By modifying the disambiguating method declaration to be a polymorphic method, we now have valid set of overloaded methods. Here, again, as in the case with parametric polymorphism, dynamic dispatch must not only choose the most specific applicable method declaration, but also infer type arguments for the chosen polymorphic method. And here, In order to infer in a type-sound manner in the presence of variance, the static type of the method call expression must be taken into account. We presented a core calculus called FGFV, which stands for Federate Generic Fortress with Variance. So this language supports multiple inheritance, parametric polymorphism, both for classes and methods, and finally, variance for the polymorphic classes. On top of this language, we formalized static overloading rules and designed a new dynamic dispatch mechanism and proved its type soundness to guarantee no ambiguous method calls and type preservation at runtime. I'll go over these three main parts one by one, starting from static overloading rules. Oh, yeah. The previous work presented informal overloading rules for a language with multiple inheritance and parametric polymorphism. They used the concept of applicable set and their subset relation and quantification over these applicable set. They required each pair of overloaded method declarations to satisfy all the three overloading rules. I'll briefly explain each rule and how we formalized it. The first one, no duplicates rule, states that distinct method declarations must have different applicable sets. Applicable set of a method declaration is a set of types to which the declaration is applicable. So this rule is to rule out the trivial cases with duplicate declarations. Instead of using the applicable set and their subset relation, we formalized the overloading rules using domain types that are existentially quantified over the method type parameters. The next one, meet rule, states that if the intersection of the applicable sets of D1 and D2 is not empty, the overloaded set must contain a method declaration D3 whose applicable set is the intersection. So this rule is for ensuring the existence of the disambiguating method declaration. And similarly, we formalized this rule using domain types of the method declarations and their intersection type. The last one, return type rule, applies when D1 is more specific than D2. That is, when the applicable set of D1 is a subset of that of D2. For a type alpha that both D1 and D2 are applicable to, the return type of any applicable instance of D2 must be a supertype of the return type of some applicable instance of D1. So this rule is to make it possible for a dynamic dispatch to find the type-preserving method instance. In our formalization, D1 is more specific than D2 if the domain type of D1 is a existential subtype of that of D2. And the existential and universal quantification over the applicable sets is represented with universal subtype relations between arrow types that are universally quantified over the method type parameters. The roles of these three rules are the same as in the previous work. So no duplicates rule and meet rule are for unambiguous method calls, and return type rule is for type preservation. Details on quantified types and their subtype relations and the fully formalized overloading rules can be found in the paper. The next thing to talk about is our dynamic dispatch mechanism. Let's revisit the sort method example again with covariant list and invariant sorted list. As we discussed, the job of dynamic dispatch is not only to choose the most specific method declaration applicable to the runtime argument type, but also to infer the method type parameters for the chosen method declaration. And here, note that the static type of the method call expression must be available at runtime and taken into account for type sound choice. For a program pi, the compiler first checks the validity of the overloaded methods. And also, in order for dynamic dispatch to make a type sound choice, the static return type of every method call expression is delivered to runtime. And at runtime, among the method declarations in a valid overloaded set, dynamic dispatch must find an appropriate instance of the most specific method declaration that is applicable to the runtime argument type K and preserve the static type G. So it tries dispatching to each method declaration in most to least specific order. So let's now look closely on how dynamic dispatch on a method declaration D for the given K and G works. Dynamic dispatch to a method declaration D for the given runtime argument type K and static return type G consists of two steps. The first step, match step, is for collecting the requirements of method type parameters that make D applicable to K and preserves the static type G. So this step collects the requirements for K to be a subtype of this parameter type and the requirements for G to be a supertype of this return type. And then, given these requirements and the initial declared bounds of method type parameters, the next step, solve step, finds the types to substitute for the method type parameters. So if the solve step finds an appropriate substitution, it means that the method declaration D is the most specific one for the given K and G, and the method call expression is dispatched to an instance of D that is instantiated with the calculated substitution. Details on how the match step collects the requirements inductively and how the collected requirements are combined and solved can be found in the paper. Finally, we proved the type soundness of our calculus FGFV to guarantee that under the static semantics defined with our formalized overloading rules and dynamic semantics based on the dynamic dispatch mechanism, there is no ambiguous method calls and types are preserved. So the key statement is that a well-typed method invocation can always be reduced by using dynamic dispatch mechanism without any ambiguity, and the reduced expression preserves the type. Of course, the theorems and proofs are in the paper. To wrap up, for a language with symmetric multiple dispatch, multiple inheritance, parametric polymorphism with variance, we formalized overloading rules and presented dynamic dispatch mechanism and proved that it works correctly in a type sound manner. Thank you very much, and I'm happy to take questions.
So we have time for a few questions.
Do you have any idea? Do you have any idea what the performance of multiple dispatch is like now?
So the question was the performance of the runtime dynamic dispatch algorithm. So yeah, there are many things that's behind this presentation, and so we had this trade-off between the performance of dynamic dispatch and the expressiveness of the language. And right now, our dynamic dispatch mechanism might exponentially blow up in some cases, but you can find it in the paper.
Other questions? I have a quick question.
Yeah.
Can you say more about the motivation for the work? I was struck as you were going through your talk that this, with multiple inheritance and multiple dispatch, that this is maybe a more challenging language to program in. Can you say more about the desirability or the difficulty for programmers for this language, this kind of language with these features?
So difficulties for the programmers for using this language.
Right. I'm wondering whether, so for example, in Java, there is no multiple inheritance in order for things to be, to solve some challenging problems. Those problems may be on the implementation side. So for example, your work has done a great job of finding an algorithm and a set of criteria that ensure that you get non-ambiguity and so on. But that's beside the point of whether this is difficult for the programmer to use to have such a powerful language. Sometimes necessity is the mother of invention. So I wonder what the motivation or of the work for adding these more expressive features, if you have any insight on that.
I think the difficulties are put in the programming language developer side. And as a programmers, I think this language is like more intuitive and to write a program, because it's intuitive for the binary method problems and
Okay, thank you.